This is example 5-6, power from a turbine. So we have a concrete dam here. In the dam we have a turbine, and then we have an inlet at A, and water flows from the big reservoir through this turbine and then out at B, and of course produces electricity in that turbine or whatever else it's used for. So we're given all this information. We're given how much water is flowing through the turbine. We're given what the height differences are, but we're also told that the turbine runs with an efficiency of 75%, right? So we're losing 25% of the power that the water is creating. And we're going to look at two different cases. We're going to look at a case where there's no frictional losses in the pipe and in the turbine, and then one where we get a head loss of 2 meters across our system. Now we know this is going to be an energy equation problem, so let's write down our energy equation. We have P in divided by gamma plus V in squared divided by 2G plus Z in plus H pump, and that's equal to P out over gamma plus V out squared over 2G plus Z out plus H of our turbine plus any head losses. Right, that's our entire setup. Now, first thing we have to do is we have to figure out where our in and our out are. Right, so what we're going to do, we're going to choose a water particle sitting somewhere up here as our in, and of course down here as our out. That would be in and out. We're not going to use A as our in because then we'd have to figure out what the pressure there is and the velocity there is and all that kind of things. It's going to be easier if we use C. You know, it's the same streamline, so we should be in good shape. So let's see. Let's look at our different values here, right? So we can say we look at pressures. If we look at C at the surface here, that's going to be 0 because it's at the atmosphere. B is also in contact with the atmosphere, so both are 0. So we can say both points A and B are in contact with the atmosphere. That means P, not beta. The P and the B combined. PB is equal to PC equal to 0. Then let's think about the datum. Right, we can do a datum that goes straight through the system here. So that means datum, not data, different thing. Datum through center line of turbine. So that gives us an ZB of 0, and ZC is going to be 3 meters plus 12 meters, so 15 meters. All right, so we have those. Now, how about our velocities? Well, the velocity at C is easy because we're in a reservoir. So we can say that has to be equal to 0. We can sneak that here in the bottom. Point C at surface of reservoir. So that means either the water level there is going to be constant or it's going to move very, very slow compared to the water that's flowing out. So we can say VC is equal to 0. I just realized that we said A and B up here. This should be, of course not A, but should be C. All right, so we have our velocity at C. That means now we want to find our velocity at B. How do we do that? Well, at B, we know we have the outflow, right, 18,000 liters per minute, and we have the diameter, so we can get Q, we can get V from Q. So we can say, well, maybe let's just get Q into the right units first. So let's say volumetric flow rate. Right, that'd be Q, and it's given to us as 18,000, that's through capital L for liters, minutes, right? So if we want to convert that, we can say that'd be 18,000 liters. Now there's 1,000 liters in a cubic meter, so we can say 1 meter cubed over 1,000 liters. And then we have minutes down here. And we, of course, have 60 seconds per minute. And if we do all those conversions, we get a Q of 0.3 cubic meters per second. Okay, we get that right. So then we can say velocity at point A. At A, we know that Q is equal to VA times AA. So from that we can find that VA is of course just going to be Q over AA. Q we're given, the area we can find by doing pi over 4 times dA squared. That simplifies to 4 times Q over pi dA squared. That means VA is equal to, if we plug in numbers, 4 times 0.3 cubic meters per second divided by pi times, what's our diameter, 300 millimeters. Writing this all for at A, it's all like for B. Let's get rid of some of these A's here and replace them by B's. That's unfortunate. Oh, let's just rewrite this whole thing here. Makes no sense to cobble along. Apologize for that. So let's try this again. Velocity at point B. All right, that was Q is equal to VB times AB, which means that VB is equal to Q over AB, which is 4 times Q over pi dB squared. We'll skip that one step there. So VB is then 4 times 0.3 meter cubed per second divided by pi times, just looked it up, so 0.3 meters squared. And that gives me a value of 4.24413 meters per second. All right, what else do we need in our equation here? So now we have, let's see, we have the pressures, we have the velocities, we have the elevations. We don't have any pumps, so we can say that's 0. No pump. means H pump equal to 0. We want to figure out what that turbine is, so we'll leave that in there. And then the head loss, right? So we have our friction loss is two different cases. Frictional loss is going to be either, maybe we'll call it HLA equal to 0, or HLB is equal to 2 meters. But those are our cases A and B. And with that, I think we have everything that we need for our calculations. So let's plug all these values into our energy equation again. All right, so we get, we said that our pressure at C at our inlet is 0. We said that the velocity is 0. We know what the elevation is, and then there's no pump, so that's also 0. Pressure at the outlet at B was going to be 0 as well. We just calculated what VB is, so VB squared over 2G. Then we said we don't have any elevation there, so 0. We want to find out what H turbine is, and then we'll have the two different HLs. So we can solve that for H turbine. Right, that's then whatever we have left over here, so that's CZ minus VB squared over 2G minus HL. All right, so let's look at this for the two different cases. So I'll say case A. No frictional loss. Or in that case, we have H turbine comma A is then going to be ZC is 16 meters, and then minus our VB 4.24413 meters per second, right? That's what we calculated above, raised to the second power, divided by 2.981 meters per second squared. And we said in this case we have no head loss. So if we plug that in, then we get a H turbine, so a turbine head of 15.0819 meters. All right, so we can see our velocity there doesn't take up all that much energy. Now if we want to get the power of the turbine, then we can say W dot, let's just do turb A, make it a little shorter. That, of course, is Q times gamma times H turbine A. And let's not forget, it said that we have a efficiency of 75%. So we have to multiply this by 0.75. Right? That means we get less power out than the water actually delivers. All right, so we can plug in our numbers, 0.3 cubic meters per second times 9,810 Newton per cubic meters times our whole thing here, 15.0819 meters. Oops, let's not forget the 0.75. And that comes out to be 33,289.6 Newton meters per second. Because those cubic meters cancel out. Newton meters per second. Newton meters per second are joules per second, which is watts, right? So we get 33.3 kilowatts. Right, so that will be the power that we get out of our turbine if there's no head losses. Now, case B will be with head losses. Case B with a 2-meter head loss. Now we could go in, plug everything back in here and do the minus 2 meters here, right, in the where we calculated turbine A. But we can also make it easier. We can just say that H turbine B in our case is just going to be H turbine A minus the 2 meters. Right, so that means we have 15 meters, so it's 13.0819 meters. And then we can do the same as we did for the power of turbine for the turbine with no head losses. So we'd have W dot turbine B is Q times gamma times H turbine B times 0.75 or 0.3 meters cubic meters per second times 9,810 Newton per cubic meters times now 13.0819 meters times 0.75, and that means we get 28,875.1 Newton times meters per second, and that is 28.9 kilowatts. All right, so by going from neglecting frictional losses to a head loss of 2 meters, we lost about, what, 5 kilowatts? 3 kilowatts, somewhere there, 29, 23, yeah, so somewhere around 10-15% reduction in our power output for our little dam here.